Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. We have just finished studying the work of Thomas Young, and now we're moving on to the work of John Tyndall. This is in Chapter 22 in A Student's Guide Through the Great Physics Texts. What I'd like to do is begin by reading through some of the biographical notes before we begin into the text itself. So here we go. John Tyndall was born in 1820 into a Protestant family in Leylandbridge in Southern Ireland. As a young man, he worked as a civil servant in the Irish Ordnance Survey and then the English Survey in Preston. He was dismissed in 1843 for his outspoken criticism of government corruption, so he went to work at a private surveyor's office. Then in 1847, he took a position as a mathematics teacher at Queenwood High School in Hampshire. Drawn to natural philosophy, he moved to Germany and he earned his doctoral degree at Marburg University under the guidance of Robert Bunsen. If the name Bunsen sounds familiar, he's the inventor of the Bunsen burner that you use in your chemistry laboratories. He then returned to England in 1851 to seek a university appointment, and in 1853 he was finally awarded a professorship in natural philosophy at the Royal Institution of London. Years later, he would succeed Michael Faraday as superintendent of the Royal Institution. We'll come across Michael Faraday next week when we study the laws of electromagnetic induction. During his career, Tyndall published dozens of scientific articles and several books. He was well known for his pioneering work on the scattering of light by atmospheric particles such as air pollutants. But Tyndall was perhaps best known for his popular scientific lectures, which drew large audiences both in England and abroad, especially in the United States, where he visited. As a member of a group of intellectuals called the X Club, along with biologist T.H. Huxley and the philosopher Herbert Spencer, Tyndall argued for a philosophy of strict scientific naturalism that was subsidized by generous public funding. And I'd only add that his agenda has largely succeeded in the sense that in most of the public schools in the United States and abroad, the scientific teachings in the schools are largely confined to scientific naturalism. That is, there's no explicit reference to God. And that's a very big difference from before Tyndall, when a lot of the scientific theories in schools that were taught had explicit references to God and the role of God in creation. So Tyndall was an opponent, for example, of James Clerk Maxwell. James Clerk Maxwell was an advocate of, I guess you'd say, natural knowledge of God. By studying nature, one can understand the nature of God. Tyndall said, not so. If you look at nature, you know nothing about God. Nature says nothing about God whatsoever. By the way, if you're interested in this kind of debate that came to a head in the 19th century, the mid-1800s, you might wish to look at a book called The Restless Clock, which came out a couple of years ago that talks about the history of this debate about the place of natural theology in the science curriculum. In any case, what Tyndall argued for was one should teach strictly an atheistic, that is non-theistic science in the schools, and the schools should receive generous public funding. And that's largely what we have in the United States today. He forcefully opposed the natural theology of leading scientists such as James Clerk Maxwell and even Isaac Newton. You might remember when we were reading Isaac Newton, he has a lot to say about what we know about God from looking at nature. In Tyndall's famous 1874 Belfast address, Belfast, Ireland, before the British Association for the Advancement of Science, Tyndall exalted the work of Charles Darwin, and he argued that science, he says, quote, shall wrest from theology the entire domain of cosmological theory. So he's saying if we take Darwin's theory of natural selection seriously, then whereas theologians had a lot to say previously about where we came from, now science is going to talk about where we came from, not the theologians. And that was something that Tyndall argued for very forcefully. Tyndall traveled to the United States in the 1870s, where he delivered popular lectures to packed houses in Boston, Philadelphia, Baltimore, Washington, and New York. The readings that are included in the following chapters that we're going to be studying this week are drawn from published versions of these lectures in which Tyndall sought to raise the wave theory of light to adequate clearness in the reader's mind and to show its power as an organizer of optical phenomena. So, despite what you may or may not think about Tyndall's kind of philosophy of science, he was extremely lucid and clear in his explanation of the wave theory of light. We're going to be looking at his lectures on the wave theory of light. So his first lecture in this series of lectures that he gave covers geometrical optics, so the study of light as being treated as lines or rays of light, and philosophical topics such as the, quote, sterility of the Middle Ages. So as you can probably guess, I'm not a fan of that idea. I think the Middle Ages were rich in ideas. Tyndall, of course, didn't think so. He thought the Middle Ages were a sterile period. So a lot of the kind of the critique of the Middle Ages that that has become popular since his time is largely attributed to people like Tyndall and others who are very critical of everything that was ancient, medieval, Catholic, and Aristotelian. The second lecture covers wave optics, that is treating light as if it was a wave, and contains a critical review of Newton's particle theory of light. So Tyndall is of course going to come down, like Young, on the side of the wave theory of light. The third lecture begins with a discussion of the relationship between the architecture or the shape of crystals and how their structure might influence the polarization of light that is traveling through them. And so we are going to start reading on Tyndall at this point. That is his chapter 4 in his third lecture. So here we go. We're on page 258 in A Student's Guide to the Great Physics Texts, and we're going to begin by looking at his chapter titled Double Refraction of Light Explained by the Undulatory Theory. So the first thing that he points out is that the speed of a wave depends on generally two properties of the medium through which it travels. So if we were to think about sound waves, for instance, what does the speed of a sound wave traveling through a medium depend on? Well, the velocity of sound is equal to the square root of the elasticity of that medium divided by the density. So E here is the elasticity, or you might say the stiffness of the medium. And rho, the Greek letter rho, is the density of the medium. And this is the particular relationship between the elasticity or the stiffness of the medium and the density. So in other words, if you make a medium very, very stiff or elastic, so there's tight bonds between the molecules of that substance, then you have a large number in the numerator under the square root, and so you have a very high velocity of sound. That would be an instance of that would be something like steel. Steel is a very stiff material, and the speed of sound is extremely high in steel. On the other hand, if you make something very dense, a very dense material, that tends to decrease the velocity of sound. Why is that? Because if you think of sound as vibrations of the medium, the more density it has, the more sluggish it is, the more inertia you might say it has, the harder it is to get the individual pieces of it vibrating back and forth, and that reduces the velocity of sound. So he starts out by saying, if we're going to be talking about waves, we have to think about what dictates the speed of waves. It's the elasticity, and that's sometimes, by the way, called the bulk modulus, if you've heard of that term, and the density of the material. And then he goes on to say that if we think of light as a wave traveling through some medium, and remember this is the idea that he's inheriting from Huygens, essentially, that there's this ether filling space, and Tyndall is a fan of the idea of ether. If there's this ether filling space, then that ether must be either a very elastic, a very stiff material, or a very sparse or a diffuse material that has a very low density. That's the only way you could have an extremely high velocity of light, either a high elasticity or a very low density. Now, he also notes here that the speed of light, it decreases when light goes into a medium such as glass or some crystals or gemstones or other kinds of media. Why is this? Well, he says that the molecules or particles of ether are not independent of the particles or atoms of the medium in which it's situated. So for example, if you have glass, there's ether, he thinks, penetrating glass, but the ether is in a sense bound to the glass molecules, and it acts on the ether, the glass acts on the ether so as to give it effectively a higher density, and that reduces the velocity of the light. So that's what, in his view, is accounting for the slowing down of light as it enters some material. Okay, and then he goes on on the next page, page 259. He's talking more about this sort of the wave nature of light and how when we can understand this wave nature of light. He mentions that in many crystals, the density is different for light traveling in different directions. He says, in virtue of the crystalline architecture that we have been considering, so in previous sections of this lecture, he was talking about how different crystals have different structures to them. So in virtue of the crystalline architecture that we have been considering, the ether in many crystals possesses different densities and hence different elasticities in two different directions. And the consequence is that some of these media transmit light with two different velocities. But as refraction depends wholly upon the change of velocity on entering the refracting medium and is greatest where the change of velocity is greatest, we have in many crystals two different refractions. By such crystals, a beam of light is divided into two. This effect is called double refraction, or sometimes birefringence. So he's kind of teeing up here to describe why Iceland crystal or Iceland spar might behave as a as if it had two different refractive indices. He's saying if the crystal structure is such that light traveling different directions experiences different elasticities, that means it has different speeds and hence different refractive indices. He'll develop this thought more in the next section. He also says in the second paragraph here that water, for example, is not birefringent when it's in its liquid form. That is, the speed of light traveling through it in different directions, it's the same. But when you crystallize it into ice, the bonds in the ice have different strengths in different orientations. It's an asymmetric molecule, an asymmetric crystal, you might say. And as a result, the speed of light in different directions will be different, and so ice is weakly birefringent. Iceland spar is strongly birefringent because it has a very different speed of light for light traveling in different directions. Okay, so that's what he's talking about in these next couple of paragraphs. This brings us to about the middle of page 259, where he says, I am unwilling to quit this subject, or to stop talking about this, before raising it to unmistakable clearness in your minds. The vibrations of light being transverse, the elasticity concerned in the propagation of any ray is the elasticity at right angles to the direction of propagation. So I want to spend a couple of minutes talking about what he means when he says that light is a transverse wave, because this is very different than what previous thinkers, such as Huygens, imagined light to be like. So let me introduce you to some terminology which you may not be familiar with. So let's talk about the difference between transverse and longitudinal waves. And I'm going to do this by means of an example. So let's suppose that we have a slinky. You might know what a slinky is. It's kind of the spiral steel hoop, right? So if we have a slinky and it's wound around like this, if we push the end of it, so we kind of push the end of the slinky like this, you're going to get a compression of the slinky where some of the coils are closer to each other, and that compression is going to kind of travel down it. And if you do this repeatedly, you can have repeated compressions, and all these compressions are going to kind of travel down the slinky like this. Okay, so this is a region of compression, and this would be a region of rarefaction or maybe expansion. And likewise, this would be a region of compression and expansion and compression and expansion. This would be if you kind of shake your hand back and forth. You send these compressional waves down the slinky. And this is also kind of how sound works, right? We talked about this before. If you press on air, you get increases in density of the air, and those travel through the air. So if we were to plot what the density or the weight per unit length of the slinky would be, the density as a function of position, you'd have here a high density and a low density and a high density and a low density, high density, and so on. And these waves would be traveling through the slinky. This, by the way, is what we call a longitudinal wave. Longitudinal wave. And what is the most perhaps important figure of a longitudinal wave is, think about if you were to color a particular point on the slinky red. So if I were to paint a point on the slinky red right here, what happens as this wave travels past that point? Well, that red point, which way is it going to shake? As the wave travels, it's going to shake to the right, and then it's going to shake back to the left. So it's going to be shaking back and forth in the, I guess if we think about this as the z direction, it'll be shaking back and forth in the z direction, a z-directed oscillation or vibration of the particles that make up the medium of travel, that make up the slinky in this case, or more generally, the medium through which the wave is traveling. The individual particles travel along the direction of the wave, in the direction of the wave. Now, I want to contrast that with a different kind of wave. I want you to imagine that you have a string, and that string is tied up, or maybe a rope, tied up to a tree. So here's a tree right here. Go ahead and make it like this. And let's suppose that you were to hold on to the end of it and shake the end of it up and down. What happens when you briefly shake it up and down? Well, you're going to get this little wave like this that's traveling down the string. So the wave travels down the string, right? But now I want you to imagine that if you were to color a particular point on the string red, what happens to that position on the string as the wave travels down the string? Which way does that point travel? Like if you were an ant even, sitting on top of the string, as this wave travels, you move up and down. So in this case, let me draw this red dot. The red dot is going to move up and down. So there is the displacement of a point in the medium, in this case, or on the string, is transverse, or we might say perpendicular, to the direction of the wave propagation. So the wave is traveling in the direction, I guess we might say in the z direction, but the displacement of the medium is up and down. This then is what we call a transverse wave. So this is what we call a transverse wave, as opposed to a longitudinal wave where the displacement of a point in the medium is along the direction of the wave transmission. So notice then, so this is kind of some background on the difference between a longitudinal wave on the one hand, and a transverse wave on the other hand. There are many examples of longitudinal waves. So if you have a slinky, that's a nice example of a longitudinal wave. If you have air vibrations or compressional waves through steel, those would be longitudinal waves. Transverse waves, I gave the example of waves traveling down a string. You might also consider the surface of water waves. If you drop a rock into a pond, the surface of the water is going to be going up and down as the wave travels horizontally along the surface of the water. So if you were to place a rubber ducky on top of the pond, as the wave travels past it, that ducky will bounce up and down. That would be an example of a transverse wave. I mean, strictly speaking, I guess you could say also slinkies, not only can they support longitudinal waves, but slinkies can support transverse waves. If you shake a slinky back and forth, well, you get a transverse wave traveling down the slinky. Okay, now why is this going to be important? I'll just give you a heads up about this and then we'll stop for now and go on, pick this up next time. There's going to be an important point here about saying that light is a transverse wave. And it's the fact that you can have polarization of transverse waves in a way that you cannot have polarization of longitudinal waves. So I'm going to try to draw a three-dimensional diagram here. Let's call this the x-axis, this the y-axis, and this the z-axis. Think for a moment about this string. If we had this string stretched along the z-axis like this, I'll use that as an archetypal example of a transverse wave. Notice that there are two independent ways that you can shake this wave, or shake the string. On the one hand, you can shake the string up and down, as I've depicted in the previous diagram. And if you do that repeatedly, you can get displacements that are vertical like this. And these are all then traveling in this direction. Okay, so they're kind of, the displacements are in the y direction according to this coordinate system. But notice also that I could have shaken the wave back and forth. So I could have shaken it this way. That is, the displacements would be along the x-axis, right? Those are also traveling toward the right, that is along the z-axis, but you have two independent ways of shaking the string. Of course, you could shake it kind of diagonally too, but you can think of diagonally as kind of a combination of horizontal and vertical shaking put together. The important thing is that the x and y axes are independent axes. X direction and y direction shaking are independent, as he will call it, polarizations of this transverse wave. There are not two different independent polarizations of a longitudinal wave. After all, there's only one way to shake a medium so that there's compressions and expansions. And that's going to be an important difference. Huygens thought that light waves were modeled as longitudinal waves, much like sound waves. Tyndall and others, Tyndall didn't come up with this idea, but Tyndall's going to be expressing this idea that light is a transverse wave, much like the waves on a string. Of course, this raises the question, what is this medium that's doing the vibrating? And that's going to have some interesting implications, but he's going to argue that light is a transverse wave.